Hello, my C105 students. So like I said, tomorrow's lecture, 29th May, Thursday, will be virtual. So I'm creating this YouTube video for you all. So this is based on Module 5, which is the chapter on gases. So I will cover the first 26 or 27 slides from Module 5 for May 29th, Thursday's lecture. All right. So let me share my screen with you all really quick. All right. So this is what your module looks like. All right. So chapter 5, module 5 is the concept on gases. These are the learning outcomes that we're going to work on. So my goal today is I'll finish at least the first 3 bullet points. All right, now, even the fifth bullet point that you see, perform stoichiometric calculations involving gas reactions. I'm going to cover that as well. The Dalton's law of partial pressure and the last two learning outcomes. I'll cover those learning outcomes during lecture on Friday. All right, so without further ado, let's get started. These are some of the important characteristics of gases, right? So whenever we think about gases, first, these are some examples of gases, right? H2 is a diatomic gas. You have hydrofluoric gas. So keep in mind, right, that HF is not really hydrofluoric acid, right? Whenever this HF gas is in aqueous form, that is when this is called the hydrofluoric acid, whereas this right here, HF, is just your hydrogen fluoride gas. All right. Then He is the group 8A inert gas. All right. So these are some of the examples. Then you have nitrogen gas, carbon dioxide gas, neon gas, and so on. All right. Now, all of these gases, they have these characteristics. So you can just read through those. All right. And the last bullet point that I wanted to look at is gases, right? If you compared that with liquids and solids, they have much lower densities. So this is the concept uh, I'm going to talk about a lot, right? How we can relate density to the PV equals to nRT ideal gas equation in a little bit. All right. So I did say those terms PV equals to nRT. Let's go ahead and define those. All right. So in this chapter, in gases chapter, whenever I say the term or use the term P, that relates to pressure. So pressure exerted by the gas molecule. All right. V equals to volume. How much space does the gas occupy? T is the temperature. And what you're going to notice is like the temperature unit that I'm going to use for this chapter is always going to be Kelvin. And I will, I don't know, first 10 or 12 slides, we'll explain why as to why that has to be the case. All right. So N is always number of moles. All right. So now we're going to talk about something called kinetic molecular theory of gases, right? So we derive all these equations, Boyle's law, Charles' law, right? P equals to nRT, ideal gas law, all right? So all of these are based on these basic assumptions. All right. The first one is straightforward. Gas can move randomly at various speeds and in every possible direction. The second one, the average kinetic energy. All right. So if you think about this, now let's say I want you to conceptualize, right? Let's say if I have a gas, let's say helium gas in a balloon, right? I want to think about how fast is that gas molecule moving in that balloon. All right. And you'll be surprised, like that gas molecules in that balloon moves at a very, 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 very high velocity. All right. Much more faster than the speed of an airplane, even though we can't see it with our naked eye, but that's how fast they are moving, right? So the average kinetic energy, K stands for kinetic energy of gas molecules, is proportional to the temperature of the gas, meaning that as the temperature increases, the kinetic energy of the gas molecules also increases. Now, keep in mind, kinetic energy has the formula half mv square, where v is the velocity of the gas or speed of the gas, meaning that we can even say that the speed of gas molecules is directly proportional to the temperature of the gas. All right. Next bullet point: a gas is composed of molecules whose volume is negligible. But the distance between them. So all of these assumptions, we hold them whenever deriving all these different equations, Boyle's law, Charles law, and so on. And gas molecules do not exert attractive or repulsive forces on one another. And finally, the collisions of gas molecules are elastic. Yes, this is the same elastic that you might have learned in physics courses, elastic collision, inelastic collision, right? So in an elastic collision, what holds true is the energy is transferred between two gas molecules or even more, right? But they are not lost. That means the energy is not lost during the collisions. Because if you think about balloon, right? So if I have two gas molecules colliding with each other, with my two small circles, whenever they collide, the energy is transferred from one gas molecule to another, and so on. That's what it means by elastic. The energy is not lost. All right. So these are some of the assumptions of kinetic molecular theory, or you can just say assumptions for ideal gas. All right. Next thing, again, to think about pressure. I think students find it hard to conceptualize pressure exerted by the gas, right? So easy way to think about this, right, is basically if I have a balloon, right? So this is my balloon. This is looks weird, but let me draw that balloon, right? Let's say I fill that up with helium gas, right? So I have helium gas here. If I have like millions of them in that balloon, keep in mind, right? So the way I conceptualize this term pressure is exerted by the gas is, for example, if I'm looking at what's the pressure exerted by the gas in the inner wall of this balloon, right? So this is my inner wall of the balloon. The way we conceptualize it, the frequency of collision, right? So how frequently are these gas molecules colliding with this inner surface tells me the pressure exerted by these gas molecules on the inner wall of this balloon. All right. And next thing, I just did bring that up in the earlier slide. The temperature is related to the average speed or the velocity of the gas molecules. Right? Basically, as temperature increases, the speed or the velocity of the gas molecule also increase. All right. All right. So thinking about gas pressure, there are different units that can be used to measure gas pressure. Right. You have PSI, right, which you might have seen whenever you fill up your car tire or even bicycle tire, right? The unit is in PSI, pounds per square inch, pound per square inch. All right. The formula for pressure, keep in mind, right, is force over unit area, right? If the force is measured in Newton, area is measured in meter squared. That's how your second unit comes into play. The third unit that we can use to measure the pressure exerted by the gas is in millimeter of mercury, mmHg. It stands for millimeter of mercury. All right, so if I place this mercury barometer, right, so this is called a mercury barometer at sea level. All right, and let's say I fill this glass ball, if you want to call it, with mercury. So what's going to happen is the atmospheric pressure is going to push this mercury. So this is my long glass tubing with one closed end, one open end. So open end is inserted into this ball, right? So at the very beginning, this glass tube didn't have anything in it. But as the atmospheric pressure presses on this mercury, the mercury is going to rise. But then after a certain height, it's going to stop. And that height is 760 millimeter. And that's where this unit comes into play, right? Millimeter of mercury. All right. If we use some other liquid, the height will not be 760 millimeter, right? Keep that in mind. So that's where the unit comes into play. And ATM is called atmosphere. That's one of the most basic unit we use to measure the gas pressure, right? And these are some of the conversion factor for you all. 760 millimeter mercury equals to 760 torr, which is equals to 1 atm, which is equals to 1.01325 times 10 to the power 5 Pascal. Pa is Pascal, right here. And again, and I'll let you know whether you have to memorize this or not. Most likely not. I think you might have, you just have to know that 1 atm equals to 760 millimeter. That's all. Other than that, all the conversion factors will be provided to you all. All right, let's start with the gas laws. The first law tells us that the pressure of a gas is inversely proportional to its volume. Right, so if you look at this, its volume proportional to 1 divided by P. That's what it means. The pressure of the gas is inversely proportional to its volume. Now, if I remove this proportionality constant right here, right, I will come up with this equation. P times V equals to a constant, right? Pressure times volume of a gas is always constant. And that's what Boyle find out. And that's why we name this law after Boyle. All right. And this is a very good pictorial depiction of what it looks like, right? Meaning that, for example, you have a pressure of 1 atm in this first setup, volume of 1 liter. If you multiply P times V, it's going to be 1 times 1, right? It's going to be 1. Right? 1 atm times liter. If you look at the same setup where the pressure has been increased to 2 atm, the volume reduces by the same factor, meaning it becomes half, since this pressure increased by a factor of 2. But again, if you look at this P times V, 2 times 0.5, will give you the value of 1 atm liter. That's what the Boyle's law means. All right, P times V equals to constant. And we can even derive this mathematical relationship whenever we are talking about different conditions, right? So P1 V1 equals to P2 V2, where P1 1 and 1 subscript is telling you that's the initial condition, if you want to call it initial condition, and then 2 is the final condition, right? And that is why some textbook write as Pi times Vi equals to Pf times Vf as well, right? Now do keep in mind, right? So for Boyle's law to hold true, right? So we talked about these four terms: P, V, N, and T, right? Pressure, volume, number of moles, and temperature. All right. Now, since Boyle's law looks at pressure and volume, right? That means for Boyle's law to hold true, the other two terms have to be constant. And that's what this means. That means N and T are constant in Boyle's law, right? All right, now the Charles law, what he looked at the relationship between the temperature of the gas and its volume, and I found out that the volume is directly proportional to the temperature, right? In other words, P divided by T equals to constant whenever I remove the proportionality sign. All right, and it's a very good depiction of this, right? So whenever you place a balloon in ice water versus boiling water, you're going to see that the volume in boiling water, which is at higher temperature, is much more larger than the volume in ice water, which is at lower temperature, right? For example, this ice water might be at 0 degrees Celsius, right? Whereas this boiling water, let's assume this is the boiling point of water, is at 100 degrees Celsius. And since volume is directly proportional to temperature, that is why as the temperature increases, so does volume. And this is a very good real life example of how Charles' law works, right? You have hot air balloon. And so I had to Google at what temperature do they usually set this hot air balloon at. And it looks like they run it at around 120 degrees Celsius. And hence the volume of that balloon so much larger, right? Whereas if I place something similar, right, a balloon, an inflated balloon in ice water, right, look at this volume going down, which is at around 0 degrees Celsius. Right, so volume of a gas increases as the temperature increases. And the Charles law can be written out by this mathematical relationship. And again, like I said, if you look at P, V, N, and T, Charles law looked at V and T. All right, that means the other two has to be constant. P and N. P and N, they are constant for Charles law. And like one last thing about Charles, the really important is the temperature, right? You have learned about temperature scale being in degree Fahrenheit, degree Celsius, and in Kelvin. Whenever we use this mathematical relationship, we always have to use the temperature in Kelvin scale. And the reason we do that, right, is basically, remember, Kelvin scale is something called absolute temperature scale. Now, what that means is basically you cannot go below 0 Kelvin, meaning you do not have negative Kelvin, right? You don't have something like -1 Kelvin or -100 Kelvin, right? Keep in mind, we do have negative degree Fahrenheit and negative degree Celsius, right? If you look at your weather app during winter, these values, degree Celsius, degree Fahrenheit, will be a negative value in December or January, right? But Kelvin can never be a negative value. That is why it's called absolute temperature scale, right? And it makes sense, right? If you look at our formula, if temperature would have been negative, right, my volume would have been negative. What the heck does that even mean, right? When volume is a negative number. And that is why the temperature always has to be in Kelvin scale. All right, now if you want to delve further, keep in mind, right? 0 Kelvin is the temperature at which all molecular motion stops. And that is why, for gas law, that's really important, right? We do need some kind of motion in gas. And that is why we have this Charles law and even any other mathematical system that we derive in this chapter, they are going to be in Kelvin. All right. So if you combine Charles law and Bohr's law, you come up with this formula. All right. P1, V1 divided by T1 are the initial condition equals to P2, V2 divided by T2. Right? And then you will work through these problems in your master in chemistry or recitation, which we will use this formula to solve some of these unknowns in the sample, right? And again, if you look at this, go back to the formula that we just said, right? Because if you go back to our first Boyle's law formula, look at that. We had P1 times P1, right? Look at that, P1 times P1 equals to P2 divided by P2 times P2. And if we look at Charles law, we had V1 divided by T1. Isn't that the case? V1 divided by T1. So we're combining these two formulas, that's all. All right, and that's called combined gas law because we combine two gases, gas laws. All right, the next law is something called Avogadro's law. So all it says is the volume occupied by a gas is directly proportional to the number of moles of gas. Or if you remove the proportionality sign, it becomes volume, right, divided by N equals to constant. Or in mathematical relationship, if you want to write it out, it's going to be something like this. P1 divided by N1 equals to V2 divided by N2, the initial condition. Here, this is the final condition. All right, and you can check this. This is a very good pictorial depiction, right? So for example, in my first set of condition, if I do V1 divided by N1, it's going to be 22.4 divided by 1, right? 22.4 liters divided by 1, which is equal to 22.4. All right, now if you increase the number of moles by adding gas, right? Let's look at that. The number of moles went to 2 moles, right? The volume increased by the same factor. But if I do the volume 2 divided by number of moles, that will give me the same value, 22.4. And that's what Avogadro's law means. All right. Now to derive the ideal gas law, we can combine all these three laws, BCA. The way I think about this is by mnemonic, right? Boyle's law, Charles law, Avogadro's law. You combine all those, we come up with this ideal gas law. In the next 3 or 4 slides, I will write down the proper equation with the equals to sign, all right? But then if you combine this is just telling you is volume is directly proportional to the temperature, inversely proportional to the pressure, directly proportional to the number of moles. All right, now next thing we're going to talk about is something called standard temperature and pressure. All right, we have a set condition, right? We call that STP, S, T, and P. All right, the temperature at standard condition is 0 degrees Celsius or 273.15 Kelvin, whereas the pressure is defined as 1 atm. Right. Now, why do we care about this? Because at STP, right, if I'm able to measure, or if I measure the volume of 1 mole of gas, or volume of 1 mole of gas, of an ideal gas to be more correct, all right, they always will have a volume of 22.4 liters. For example, at STP, if I have 1 mole of helium, or if I have 1 mole of xenon, or if I have 1 mole of methane or CS4, they all will hold a volume of or have a volume of 22.4 liters. And that's called the molar volume at STP. Right? Now, how do we come up with this, right? Now, in the next slide, I'm going to show you is this formula, V proportional to NT divided by P, all right, can be rewrote as PV equals to nRT. All right. Then if we plug in the values, right, at STP, we have the pressure of 1 atm, right? Volume is our unknown. Number of moles, since we're talking about 1 mole, is 1 mole. R is a constant. The constant value will be provided to you. Temperature is 0 degrees Celsius, 273.15 Kelvin, right? If you solve this equation, the volume will be 22.4 liters. And that's how the scientists are able to derive the molar volume at STP. All right, so this is what I was talking about, right? So whenever you remove the proportionality sign, volume is directly proportional to N times T divided by P, right? So if you remove the proportionality sign, a constant gets added called R, right? So it's going to be something like this, V equals to N times, so this is my constant R times T divided by P. And then I can rearrange the equation, right? I multiply both sides by P, and I end up with PV equals to nRT, and this is called our ideal gas law, right? Now, R is a constant, and depending upon what problem that I'm working through for this chapter, I think most of the time, right, we'll, at least the next 10, 15 slides, we'll use this R value, right? But for example, if we look at the gas velocity calculation, we will be using this R value. And I will go over as to why we use this constant versus this constant, right? It's the same as someone telling me, oh, if 1 inch equals to 2.54 centimeter for a particular problem, I might use 1 inch, right? For another problem, I can use that 2.54 centimeter, right? Depending upon what question is asking me, all right? All right. Now, if you look at the top unit, right, we have R equals to 0.08206 liter atm per mole times Kelvin. To derive this unit, all right, in our ideal gas law, the pressure has to be in atm, the volume has to be in liters, temperature has to be in Kelvin, all right, and N is always in moles. How does that work? What's this? So this is our formula, P equals to nRT. I'm going to write down all my units. P is in atm. Volume is in liters. Number of moles is in mol. My R is my unknown, right? So I'm trying to figure out the unit for R. And my temperature is in Kelvin. So if I solve for R, what you're going to see is R equals to liter, sorry, let me do that in red, liter times atm divided by mole times Kelvin. And look at that. Isn't that the unit for R? Right? And you can use this technique for any physics or biology courses, right? That you will take where you do this something called unit analysis, right? To figure out the unit of anything, right? For example, let's say if you know that force equals to mass times acceleration, right? And if I have to figure out what's the unit of force that we can have, I know that mass can be measured in kilograms, right? Acceleration can be measured in meters per second square, and that's how I know that, oh, force has a unit of kilograms times meters per second square. And that's what I did here, all right, to figure out the unit of R. All right, again, this is more like telling you what is the constant in your Avogadro's law, all right, and so on. And so going backward as to how are these two related, how are these two related, how are these two related, right? Right now, let's look at some of the gas laws problem, right? I went over all those laws, all right? Now, a couple of things to keep in mind, right, is the first one, right, as to whenever you have been given these kind of questions, right? Pressure is decreasing, volume is increasing, temperature of gas is raised to, meaning you have two sets of conditions. That is when you use the individual gas law, right? For example, for some problem, you might be able to use P1, V1, equals to P2 V2 whenever they talk about pressure and volume, right? And use that formula, all right? Or you can use the Charles law mathematical relationship or the Avogadro's law mathematical relationship, depending on what the question is asking you, all right? But for ideal gas law, right, PB equals to nRT, this will be the case, right? Meaning that out of this 1, 2, 3, 4 variables, 3 will be provided to you. You will be asked to solve for the fourth. And that's how you know you'll be using this versus one of those individual gas laws, right? And again, one of the other most important thing is watch out for units. Really, really important in chemistry, physics, biology, right? All right, let's work through some of the problems now, all right? All right, so now if I look at this question, now again, this is definitely, if you look at this question, slightly challenging because it's kind of giving us, it's hard to read whether they have given us two set of conditions or not, right? So now, but then I look at this like, oh, they have told me that the sample of nitrogen right here occupies this much volume at this much temperature under this pressure, right? And then it's asking me what volume would it occupy at STP. And as soon as I see that, I know that at STP, right, my temperature is 0 degrees Celsius, the pressure is 1 atm. So that tells me that things or the condition have changed. When the condition change, that's how I know I have to use one of these combined gas laws or the individual gas laws. All right, so let's work this problem out. Let me do that in the whiteboard. I might have more space here. All right, so now if you look at that problem, my initial condition, right? So I'm going to write down my initial condition here in red. And my final condition, which I know is at STP, standard temperature and pressure. All right, because they have asked me, my question is, what volume would it occupy at STP? That's how I know this is my final condition. And the first part of the sentence is my initial condition. Now, all I do is write down everything that I know. For my initial condition, I know that my temperature is 75 degrees Celsius. Change that to Kelvin, you're going to end up with 348.15 Kelvin. All right. At STP, my temperature is 0 degrees Celsius, right? Which is equivalent to 273.15 Kelvin. All right. Now, the volume has been given to me as 750 milliliters of nitrogen. I'm going to directly convert that to liters, and I'll let you know why, or do we need to keep this or change the milliliters to liters in a little bit. All right. My volume 2 is what I'm trying to find out, right? And finally my pressure, first set of condition is given to me as 810 torr, right? And I'm going to convert that to ATM. And again, the reason I'm doing this is like to get a hang of, because whenever I use the PV equals to nRT equation, I will have to use the pressure in ATM. And that is why I'm doing this. For this problem, you do not have to convert the torr to ATM. Keep that in mind, right? Because when I write on the formula, you're going to see why, right? But again, I'm trying to do this so I get a hang of, or I know that I'm converting these torrs or pressures to ATM. 1.0658 ATM. I repeat, you do not have to convert the pressure for this problem to ATM. All right. And one of the reason I'm doing this is you start getting a hang of how to convert one unit of pressure to another. All right. And my pressure 1 or pressure 2 is given to me as 1 ATM, right? Because it's my STP, meaning that my pressure is given to me as 1 ATM. Oh, now all I know is, oh, looks like I had P1, V1, T1. I have T2, P2 value. I'm trying to figure out V2. And the only equation that we know is combined gas law, right? Which tells us P1, V1 divided by T1 equals to P2, V2 divided by T2. Like this, I put in all my values, right? So 1.0658. And I'm not going to write down the unit, but I'm going to keep track of them, right? Temperature is 348.15 Kelvin equals to pressure 2, 1, volume 2 is my unknown. My temperature is 273.15. All right. Now what's going to happen is, like, if you do the math, right, the unit over here, 1.0658, that's in ATM, right? This is an ATM, is going to cancel out with this 1 ATM, right? My Kelvin here, so this is my Kelvin here, is going to cancel out with this Kelvin right here. I converted the milliliters to liters. That is why my final unit will end up being in liters. My V2 will be in liters. All right. If you do the math, I will end up with V2 being 0.627 liters. All right. Now, a couple of questions, like thoughts for you all, right? Remember, here I did not have to convert my P1 to ATM. If I just put in this 810 torr and then 1 ATM equals to 760 torr, as long as I'm consistent with both of those, I would have ended up with the same answer, right? So I could have used 810 torr and 760 torr. Or you're like, no, I'm just going to convert this torr to ATM because my STP value is in 1 ATM. That is why. It's up to you. But using 810 torr and 760 torr will get you the answer. Now, question for you all, right? Can I leave this degrees Celsius as it is? All right. Work that out. Think about it. All right. And what you're going to see is, no, we cannot. Because remember, there, to convert from degrees Celsius to Kelvin, we did not multiply or divide that 273.15, right? We add 273.15 to go from degrees Celsius to Kelvin. And that is why we cannot do that. And for any gas loss problem, please make sure that the temperature has to be in Kelvin. And that's how you answer this question. All right. Now, where you're going to head next is the PV equals to nRT is an interesting equation, right? Because so far we have worked through where we have pressure, volume, and you're gonna, whenever you start working through this gas loss problem, you're just gonna start by warming up by looking at these, right? PV equals to nRT, you're gonna look at those individual gas laws. Then the next thing we're gonna look at is how can we include mass in this equation? All right. So what I mean by that is, so if you look at this question, all right, now it tells us everything, right? It gives us the volume here of the carbon dioxide gas that is collected. It gives us the pressure here. We've learned about that. It gives us the temperature here. That's good. But if you look at the question, it's asking me how many grams of carbon dioxide. All right. But we know that, right? If you look at this, if we have a gas and if we are able to figure out the number of moles of that gas, for example, let's say my gas is N2 gas. If I figure out the number of moles of gas, I know my molar mass of N2, right? I go to the periodic table, figure out my molar mass of N2, and guess what? I can use these two values to figure out the mass of N2, right? And that's what we're gonna do for this problem, right? So I'm gonna read this question. My thought process is, okay, I'm gonna use the PV equals to nRT equation because my volume is given here, right? My pressure is given here, my temperature is given here. I can use the PV equals to nRT equation, right? Then I'm going to figure out my number of moles first. Since we talk about carbon dioxide, I can figure out the molar mass of carbon dioxide. And once I find that out, I'll be able to find out the mass of carbon dioxide. All right, let's go through this problem now. All right, so for this problem, all right, first time write down the equation just to show you what it's talking about, right? It's talking about calcium carbonate decomposing into calcium oxide and carbon dioxide gas. Now, if you read the question, it's focusing solely on carbon dioxide gas. It's the data given, right? Because it says after the decomposition is complete, the gas has a pressure of this and temperature of this, right? And the flask that it is collected in has a volume of 250 ml. All right, that means the volume of carbon dioxide is also given to me. And that is why I'm going to focus on carbon dioxide first. Because first thing, as soon as I see this equation, I make sure that it's balanced, right? If it's not, I'm going to balance it. It looks like the reaction is balanced, right? One calcium atom on my reactant side, one calcium atom. On my product side, three oxygen atoms on my reactant and product side as well. So this reaction is balanced. Same thing with carbon, all right? All right, now if you look at carbon dioxide, since we're talking about carbon dioxide, the values given. Volume is given to me as 250 milliliters, which is 0.250 liters. My temperature is given as 31 degrees Celsius. You convert that to Kelvin by adding 273.15, and that will give me 304.15 Kelvin. The next value that is given to me is the pressure. Pressure is given to me as 988 torr. I know my conversion factor. 1 atm is equivalent to 760 torr. And then my pressure ends up being 1.3 atm. So now I'm going to use my PV equals to nRT equation, right? Because in this equation, I know everything except for my number of moles. So let's plug that in. My pressure value is 1.3 atm. My volume value is 0.250 liters. I'm going to tell you why I'm using all the liters for this problem in a little bit. My N is my unknown. Now my R. So I have those three constants, right, for R. Now the question is what constant to use. If we go back to the slides, my R can have these different constant. This constant, this constant, and this constant, right? But if you look at the unit, this right here is always used for the ideal gas law. Right? So I'm going to use that unit 0.08206 liter atm divided by mole times Kelvin times my temperature is in Kelvin, 4.15. Now, what's why this constant with this unit works, right? So if you look at this, what's this? Unit wise, right? My ATM is going to cancel out with my ATM. My liter will cancel out with my liter. My Kelvin will cancel out my this Kelvin. And the only unit that's left is mole, right? Which is going to go to the other side of the equation. And look at that. N has a unit of mole. And that makes sense. And that is why we use this constant. Now, if you solve for N, you'll end up with 0.0130 mole of carbon dioxide. All right, my molar mass, which I'm going to start using this short form for molar mass of carbon dioxide. You add up the atomic weight of carbon and two oxygen atoms. You end up with 44.01 gram of carbon dioxide is in 1 mole carbon dioxide gas. Now guess what? I can combine these two, right? This and this to figure out the mass of carbon dioxide. All right. Now again, it's up to you what you want to do. There's two ways to go about it, right? You can either use the formula molar mass equals to mass over the number of moles formula, or you can use something called unit analysis, right? Where what I do is, okay, this is my given data. This is my conversion factor. And what did I teach you? Given data times conversion factor is your final answer. So given data is 0.10130 mole CO2. My conversion factor is 1 mole CO2 weighs 44.01 gram of CO2. And the beautiful thing about this is the mole of carbon dioxide cancels out with mole of carbon dioxide. We are left with mass of carbon dioxide, which will give you the answer 0.572 gram. All right. So again, take your time, right? Run through this question. This is slightly challenging because we are infusing two different concepts, right? PV equals to nRT concept with this thing that you've learned, right? Because you've learned how to convert if you have given the moles, how to go to mass in this problem. So you're infusing two different concepts for this problem. So sit down, take your time, all right, and then work through this problem. All right, hopefully this makes sense, all right? Which problem did I work through? I worked through this problem, right? So what I did was I used the ideal gas law, and then moles to mass concept. From the ideal gas law, I was able to figure out the number of moles, which is n, right? And from n and molar mass, I was able to figure out the mass of carbon dioxide, right? Now the last slide, maybe not last slide, I have to go through 2 or 3 more slides, right? But one last numerical problem though. Right. So maybe, sorry, 2 numerical problems. All right. Now, again, next thing here, what we're going to learn is we're going to combine the gas laws here with our percent mass percent combustion for problems, right? So last week, or maybe 1.5 week ago, we went over how to figure out the mass percent of each element, right, in a given formula, right? Then we learned how to derive the empirical formula, right? And then now here's talking about STP as well. So that tells us that we are infusing or combining these two concepts. All right, so let's look at this problem. So it says a compound that contains only carbon and hydrogen is 80.0% carbon and 20.0% hydrogen by mass. All right, so as soon as I see this, my first instinct is going to be to figure out the empirical formula. All right, meaning that if you are given 100 gram of the sample, all right, we said that, oh, this is the same as 80.0 gram carbon, 20.0 gram hydrogen, All right, then we use the molar mass to find the number of moles and divide by the smallest number. And then if you do that, what you're going to do is end up is the empirical formula of CS3 from the first sentence of this question. We're going to go over it, make sure you work through that part, and then make sure you understand how you derived the CS3 value. All right. Then what I'm going to do is, okay, that's good. I know the empirical formula, but my question is asking me for the molecular formula of the compound. All right. So now, next thing I'm going to do is I will figure out the number of moles of this gas, because they have given me that the condition is STP, the volume is given. All right. At STP, we know the temperature, we know the pressure, and I'm able to figure out the number of moles, right? And I can use the number of moles and this mass given to find the molar mass. And we learn how to use the molar mass and the empirical formula mass to figure out the molecular formula. All right, so let's bear with me and then we can slowly work through this problem. All right, again, first thing, I expect you to work through the first part to derive the empirical formula as CH3. That's your job, right? Now let's look at the STP condition. Since talking about STP, my temperature is 273.15 Kelvin. My pressure is 1 atm. Right? They've told me the volume is 546 milliliters. V for volume. You change that to liters, you end up with 0.546 liters. All right, so I'm going to use that formula PV equals to nRT and figure out the number of moles. So if you plug in all these values, all right, where R equals to 0.08206, my N will end up being 0.02436 moles. So what this is telling me, right, this compound, right, which has gas, right, which is a gas itself, has these many number of moles at STP. All right. So that's what I figured out. Now, why did I figure out the number of moles? Because, like I said, if you think about this, my mass has been provided to me here. It tells me that the mass of the gas is 0.732 gram. The mass has been provided to me as 0.732 gram. Now, how do I find molar mass? Remember, my molar mass is always equals to number of moles divided by mass. And that's why the unit grams per mole, right? All I do is I plug in the values. Number of moles is 0.02436 divided by 0. It should be grams per mole, right? Oh, shoot. Now, is this formula correct? No, I messed it up, right? Because number of moles can't have the unit grams, right? That means I made a mistake. Let's go back and correct my mistake, right? It should be mass over number of moles. Mass over number of moles. Because if I have the formula, then the molar mass will have the unit grams, which is the unit to measure mass. Moles, unit to measure moles. So let's just fix this as well. My mass is given to me as 0.732 gram sample and 0.02436 mole. That's my molar mass, which is going to be 30.0492. 30.0492 grams per mole. Right. Now, this is the molecular formula of the actual gas, right? Now this was my empirical formula. That means my empirical formula, empirical formula, molar mass. All I do is I add one carbon and three hydrogen atoms. I end up with about 15 grams per mole, right? And if you recall, what we did next was figure out our N value. My N value we figured out by taking the molar mass, dividing that by the empirical formula molar mass. So if I divide 30, I'm going to roughly take this number. I will end up with 2. The last step is take that empirical formula, multiply that by our N, meaning that all the numerical subscripted are multiplied by 2. So that ends up being this gas. That means the gas that we were looking at, or the question was talking about, is C2H6. All right. So that's going to be our molecular formula. This is definitely, I would say, a challenging concept because remember, we are bringing together what you've learned 1.5 week back and then combining this with our STP or ideal gas law concept. All right, definitely take your time and then run through this problem again, right? On a blank sheet of paper, work through this problem, see if you're able to work through it or not. All right. All right, the last concept before I end this slide is the gas density concept, right? So the idea behind this, right, and then is I just told you, right, my number of moles is mass over molar mass. How did I get this formula? Remember, I told you just that molar mass equals to mass over number of moles. So if I rearrange this equation, I will end up with this N equals to mass over molar mass, right? From my PV equals to nRT formula, if I rearrange the equation, my N value will equals to PV divided by RT, right? N equals to PV divided by RT, isn't it? Now, if I combine these two, I end up with this formula right here, right? And if you, in that formula, M over V, density equals to mass over volume. Look at that, mass over volume. That is why the ideal gas law or the equation can also be written in this form, right? Molar mass equals to density times gas constant times temperature divided by P. Right? This is how the ideal gas law relates molar mass and density values. Right? Right. One last problem, stoichiometry involving gases, and then that'll be it for this video. All right. So we talked about stoichiometry during the last 2 lectures. Now we're going to see how stoichiometry can be infused or combined with our ideal gas law. Right. So for example, it's talking about airbag. The airbag that you use in the car, that we use, or the company places in the car, has this compound called sodium azide. All right. And as soon as you have an accident, just to make sure that you are safe, this compound decomposes into sodium solid and then nitrogen gas. And that formation of nitrogen gas is what inflates that airbag and saves your head and then probably saves you from fatal injury. All right. Now it's telling us, okay, this much sodium azide was used in the airbag to produce N2 gas, and that N2 gas, which is going to fill up the airbag, right, has a volume of 45.5 liters and is required to have a pressure of. So it's given us the pressure of the N2, the temperature at which the N2 is going to be, right? Then it's asking us what quantity of sodium azide, which is this, should be used to generate the required quantity of gas, which is 45.5 liters. All right. For example, let's say if I'm a chemist, right? Again, the goal is to release this nitrogen gas in that airbag. But then we need to have an idea, okay, that's good, but then how much of the sodium azide should we place in that air bag, all right, to give us nitrogen gas that will have a volume of 45.5 liters. All right, so let's work through this problem, and then that will be the end of this. All right, so again, we are looking at our N2 gas and the values that have been given to us for N2. All right, the volume has been given to us, 45.5 liters. All right, my pressure is given to me as 829 torr, and I think by now you know how to convert that torr to ATM. All right, my temperature is given to me as 22.0 degrees Celsius. If I convert that to Kelvin, it's 295.15 Kelvin. All right, so I'm going to use my PV equals to nRT equation. My R is a constant, meaning everything is known except for the number of moles of N2. And I solve for this. My N will end up being 2.06046 mole of nitrogen gas. Right? Now we're going to use this stoichiometric ratio to figure out, okay, I know the moles of N2 gas, right? Now my goal is to figure out the mass of NaN3, right? So first I'm going to use this stoichiometric ratio of 3N2 can be produced from 2 moles of NaN3, right? Then I can use the molar mass of NaN3 to find the mass of sodium azide, right? So my stoichiometric ratio tells me that 2.046 mole of N2, right? My balance reaction tells me 3 moles of N2 can be produced from 2 mole of NaN3. All right. Now my last step is NaN3. If you figure out the molar mass of NaN3, it ends up being 65.02 grams per 1 mole. So 1 mole of NaN3 weighs 65.02 gram of NaN3. If I say it up this way, the mole of N2 cancels out with mole of N2. The mole of NaN3 cancels out with mole of NaN3, and in the end, I end up with grams of NaN3, and that is what this question is asking me. 88.6 grams. And again, these numbers might vary, right? It might be 88.0, 88.2, or 88.4, 88.9, depending upon the conversion factor here. Because some of the textbook, or at least whoever solved this problem, because might have used either 273 to convert this degree Celsius to Kelvin, right? So that might be the reason this answer might vary slightly, right? Because whenever I used 273.15, I got 88.6 gram. But again, it's the same concept that you have to follow. Figure out the number of moles of N2, then use the stoichiometric ratio, right? Figure out the number of moles of NaN3, sodium azide, and then finally use the molar mass. And the idea is, again, data given, right? But again, that data here, you have to figure out by using the PV equals to nRT equation. Times the conversion factor will get you the answer. All right, so I'm going to stop here. And during the next lecture, I'm going to start from slide number 29, Dalton's law of partial pressure. And my goal is to finish all the slides all the way to up to slide number 47. All right, so again, make sure you watch this video before you go to the registration session. That's going to help you a lot, right?